Okay, so this is HPC seminars, and I'm going to talk today about HPC in physics. My name is Ruben Butiarja. I work with scientific computing at NICS, at National Institute for Computational Sciences. And since physics is such a broad subject, and my background is in astrophysics, so today I'm going to talk mostly in astrophysics. And I'm just going to give some overview about the kind of research we do in astrophysics, especially the one that's going on here at UT and with the collaboration with RNL. And I'll talk a bit about how computer simulation can help with theory and experiments. Now simulation is pretty much the part of the three pillars of science. So I'll introduce you to this phenomena in physics called gravitational wave. And another Marcia Bartusiak mentioned this is one of an Einstein unfinished symphony, because this is probably one of the last predictions of Einstein's general relativity that has not been directly tested. So according to general relativity, which Einstein came up with in 1915, gravity is not a mysterious action at a distance. So in Newtonian world, gravity is an action at a distance. But here basically says that gravity is the effect of the space-time curvature due to mass. And we have an illustration of the Earth making a curvature in the space-time. The consequence of that is an accelerating massive object produces ripples of space-time curvatures, and this is called the gravitational wave. So gravitational wave has not been directly detected, but detectors are either online already or coming online, and some of them, for example, is LIGO, and then also it's being upgraded to advanced LIGO. And Virgo is a collaboration for gravitational wave detection in Europe, and this is a picture of LIGO in Hanford and Virgo. And so the point is that because gravitational wave is actually a ripple in space-time itself, it can propagate unabated by matters and can help us see the kind of thing that we cannot see, which is electromagnetic waves. So gravitational wave would be a new novel way to see nature, complementing visible light, complementing infrared, X-rays, and ultraviolet that we've seen so far. So, sources of gravitational waves. So here is the plot to show the sensitivity of some of the detectors to kind of gravitational wave source. And for example, advanced LIGO can detect rotating neutron stars and supernova protoneutron stars that produce gravitational waves. So one of the difficulty in detecting gravitational wave is that gravitational wave is very, very weak, and so it's just up to recently that we are advanced enough, or we have equipment advanced enough to be sensitive enough to detect this kind of gravitational waves. So these are a few of the strongest sources of gravitational waves. So, but because detection is so difficult, this kind of experiments requires gravitational wave templates. So the kind of frequency and spectrums to extract the signals from background noise. As you can imagine, to detect something so sensitive that there are a lot of background noise. And so where do we get this template? It's from HPC simulation to simulate this kind of phenomena to help the experiment detect the gravitational waves. Talk a bit about this simulation in this type of object realm that produce gravitational waves. So I switch and say about neutron stars. So what is neutron star? Neutron stars is a dense object left behind by core collapse supernova. And later on, I'll talk a little bit more about core collapse supernova. So neutron stars have a mass about 1 to 1.5 solar mass, compressed to about 10 kilometer radius. So here I have a map of Knox field with 10 kilometer radius, and you can imagine compressing our sun to this radius. They produce an object with a very extreme density, and one of the analogies one of sugar wave tons in neutron stars is because it's so dense. So neutron star has been discovered as both solitary objects, as pulsars, which is a rotating neutron stars with a very high magnetic field, and in binary systems. So binary neutron stars doesn't maintain its orbit forever, because with binary neutron star orbiting, it loses its energy to gravitational wave emission. So eventually, binary neutron star will in spiral and merge. So that's the kind of thing that produces one of the strongest gravitational waves. Binary neutron star mergers is associated with a host of other phenomena. So we know that we've detected gamma ray burst, which is a very strong burst of gamma rays from a cosmic origin, and a binary neutron star is the candidate of this gamma ray burst progenitors. And also, binary neutron star it's been thought to be the type where our process nucleosynthesis happens. So model binary neutron star in HPC requires very sophisticated software tools. So this is the kind of ingredients that you have to have in your code to be able to model binary neutron star merger. You have to, of course, fluid evolution, if we represent the stars as fluid, and you want magnetic fields in the fluid because neutron stars are usually magnetized, and you want nuclear physics, of course, for the equation of states of the neutron star itself. It requires some sort of a gravitational self-gravity treatment, either Newtonian with some general relativistic correction, or a full general relativistic implementation in your code. Hopefully, we have some radiation transport, and this is inherently three-dimensional phenomena. So your code to be able to handle 3D. And there are, in the neutron star, there are different length scales that need to be resolved. You have the star surface, and you have the orbital length scale, and then you also have the outer boundaries where if you want to extract gravitational wave signals, that would be your simulation to be large enough so that your boundary condition doesn't affect the dynamics of your simulation. So to deal with some of this multi-scale, then we can deploy a technique called adaptive mass refinement. Basically, you put higher resolution only where you need it. So of the simulation that's been done in neutron star merger has been some sort of a simplification of all or some of this. So this would be the ideal simulation, but of course it takes a lot of efforts and a lot of computational costs to do this. To try to handle with some of this, there's a collaboration here with Nix and with Progress to develop a new code called Genesis. And the initial target for this code is for simulation of neutron star mergers and core collapse supernovae. And this code is written entirely in modern Fortran, in Fortran 2003 and 2008 standard. It's meant to be modular and it's meant to be extensible, and we accomplish that by using object-oriented design. And this is Union-based or grid-based code, and we have implemented some of the physics software that I mentioned earlier, and we have also some initial AMR capability in the code. So, the of Genesis, we use domain decomposition, where we basically decode our mass into multiple trips, and that's distributed over different processors. And this is just a simplified example where we have 27 processors, and you can see here the numbering is basically the processor assigned to work on this grid. And so for each of the grid, we need to solve. For example, here I showed the fluid evolution equation that needs to be solved for each point on the grid. Of course, there are equations that needs to be solved to do simulation. So, obviously, developing a lot code base is not easy. We have to guard against unintended bugs. So Genesis used what we call the test-driven development. Basically, for each module, we will have test problem to make sure we check for correctness, and that it can solve the correct equation. This is just some of a illustration of the kind of test problem that has been done in Genesis. So this also to ensure that when we run our production simulation, that we get correct result, or the result that we intend. The scaling of Genesis, basically we show here that we can do weak scale up to more than 100,000 processors. So weak scaling means that how the solution time varies as we increase the number of processors given a fixed problem size. So the point of scaling is that you can solve bigger problem by adding more processors, and hopefully you maintain more or less constant time to solution. Let me show you an early neutron star merger simulation that we've done in the past. We use hydrostatic polytrope as a simplified model for neutron stars, and for each star we give just an initial velocity for Keplerian orbit, and since we implement gravitational radiation losses, then it starts in spiral because it produces gravitational wave emission. I'm going to switch here. The stars start in spiraling, and tidal effects start to take over, and then the star merge and rings down happen, and now become a massive mass. Right? Okay. Initially, it starts as a point mass orbiting, and then tidal effects start to take over, and the star starts to merge. Okay, from that simulation, we can extract gravitational wave signals. So here's an example of a gravitational wave from that simulation. I think the gravitational wave approximates very much like the point mass. So if you just have 2 point mass orbiting, and this will be the kind of, the dotted line here will be the kind of gravitational wave that it produces. So if you have 2 point mass orbiting and then losing its energy to the gravitational wave and merge, this will be the kind of signal. But since this is so the next step here, you start seeing it's the in spiral of the neutron stars, where it doesn't approach the point mass approximation any longer. And then here is the signal when the merger start to happen, and that's followed by the ring down, and then eventually gravitational wave production ceases because the mass is moving in symmetrically. So this is a kind of it's a kind of simulation where simulation inform experiments and help experiments in science. So the next topic I'm going to talk about is a core collapse supernova simulation. So core collapse supernova is a death throes of massive stars. So a mass with more than 8 to 10 solar mass at the end of its life will collapse and explode to produce one of the most powerful explosions in the universe, called core collapse supernova. So 10 to 50 Earth of energy is produced in this core collapse supernova. 1% of it is kinetic energy, and the most of it is a neutrino radiation. This occurs about twice per century in our galaxy, and the more important thing is that core collapse supernova is the dominant source of elements in the universe. So you see in the periodic table, all that the blue color here is produced in the it's thought to be produced in the event of the supernova itself. The yellow color is produced in large stars, which is basically the progenitors of core collapse supernova. So it's really core collapse supernova is one of answers to questions relating to our origins in the universe, because without these massive stars and without the explosion to spread the kind of elements cooked in the stars, life as we know it would not exist. So how does happen so a massive star burns hydrogen and helium for most of its life, and it continues to burn carbon, oxygen, and magnesium, and then near the end it has an iron core with silicon and other elements layers. So after a while, because the iron core is so dense, the electron degeneracy principle can no longer hold, and you don't have any more nuclear reaction happening in the iron core. The core starts to collapse, and it collapses. It goes through extreme density until at some point, because the strong nuclear force, it cannot collapse anymore. And at that point, the core bounces, and it launches a shock wave that will eventually disrupt the whole star. But as the shock wave going outwards, there's incoming materials going inwards that eventually stalls the shock wave. So the question in core collapse supernova research is how the supernova stalls shock wave revive. So this has been an ongoing research in the last of 4 or 5 decades, and the elucidation of this mechanism is still investigated. But I'm going to stop there and actually talk about this stall shock wave. So it turns out that the stall shock wave is unstable against non-radial perturbation, and this has been named SASI, Stationary Accretion Shock Instability. And in fact, SASI has been observed in supernova simulation, but the first discovery of SASI is actually in the simulation, in computer simulation itself. So this may be the key ingredient to a robust supernova simulation. So again, this is an example where computer simulation actually informs the theory of the core collapse supernova. One of the questions we ask is that we know that from supernova we have neutron star and pulsars. Pulsars have a very strong magnetic field. Well, most stars or most supernova progenitors have a weak magnetic field. So how does it get from here to pulsar with strong magnetic field? And we know that magnetic field amplification usually relies on fan rotation. But we know that most star's progenitors are only slowly rotating. So then another issue is that the role of magnetic fields in supernova dynamics is not clear. But know that stars have turbulence, and turbulence is usually the textbook example of how magnetic field can be amplified. So we ask the question, can SASI amplify the magnetic field of the progenitor stars? What we found is that magnetic field is actually amplified exponentially in SASI. So again, I mentioned earlier, this is an example where computer simulation informed theory of or developing theory of core collapse supernova. So we ran an experiment where we put magnetic field on a star supernova shock, and we just run the movie. Here you see a plot of or a volume plot of magnetic field, where the more opaque is the stronger magnetic field, and this color here also tells you the strength of the magnetic field. So we perturb this initial condition non-radially, and we start seeing that SASI is developing. We start seeing a slotting motion because of SASI, and because of the compression, we start seeing the magnetic field build up around the axis. And then here we start to see the nonlinear SASI, where basically there's rotation and there's turbulence. And here the slides follow the plane of the angular momentum, and you start seeing the magnetic field start to build up on this due to this turbulence of the SASI. So you see more and more of this magenta color. You run that one more time. All in 1 second of physical time. Through the slices, here is the slice of parallel to the XZ plane. At the thing we see the magnetic field start to build up around the axis because of the compression when the SASI start to oscillate. But as more and more falling material from the supernova start to impinge on the stars, we start seeing rotation, and because the falling material start to hit this in an oblique angle, and here we start seeing rotation, and now the slices here is that the plane is normal as parallel with the angular momentum, and we start to see more build up of magnetic field up to the 1 to the 15 or 10 to the 15 Gauss. And also notice here that the volume of this surface has expanded from 100 kilometers to 200 kilometers. We know the kind of mechanism that amplifies the magnetic field is primarily due to stretching. As turbulence happens, the same or elements that connected get stressed, and since the magnetic field is frozen in the fluid, they get stressed too, and that produces the magnetic field amplification. And as actually what we also find out is that we can resolve the amplification or the amplification stops because we can only do finite resolution. So here we run the simulation with 2x of the resolution on the right hand side, and you see that there are more magnetic fields when we increase the resolution. But we can increase more resolution to completely resolve the magnetic field amplification because the computational cost. So this simulation, for example, is run with 64,000 cores on Jaguar. So in my last movie, I want to show you what happened when at the end of that simulation, we have shock surface and we have magnetic field, and we sit randomly on the surface and then trace out the magnetic field line, and we can see the structure of the magnetic field on the proto-neutron stars. This is the shock surface, and we randomly sit the shock surface, and then we trace that sit based on the magnetic field line. Very a complex structure of magnetic field on the proto-neutron stars. So that's what I have, and Junji will talk some more about different kind of HPC in different physics brains.
For the second part of the talk on HPC in physics. My name is Junqi. I'm also from NIX Center, and I work in the field of condensed matter physics. Specifically, I'm interested in the phase transition and the critical behavior, such as structure transition and magnetic phase transition, etc. So the outline of the talk is as follows. First, I will show why HPC is necessary in this field, and I will talk about the typical two approach. You can use numeric method or simulation depending on the problem, and the most two popular simulational methods, molecular dynamics and Monte Carlo simulation. After that, I will show you a case example, a code called WLLSMS, and we're going to use this code to study the magnetic phase transition of iron. After that, I will summarize. So for Ruben, in his talk, he mentioned this triangle several times. I don't know where this originates. Maybe it doesn't matter, but I copied this thought actually from this book. So David Landau and Kurt Binder are two pioneers in Monte Carlo simulation. And in the community, and David Landau tried to push this diagram, which mentions that simulation method as the third branch of methodology to study nature, and the people in the field like to call it the Landau triangle. So why is it necessary to use high performance computing in this field? Okay, let me give you a a simple example. Let's say we want to study water. Water is a common matter on Earth. Water is the basic of life. So we want to understand some of peculiar properties of water. For example, why the solid phase of water, ice, is less dense than the liquid phase, and how is the ice melt into water? What's the details? What happened there exactly? So let's start simple. That's how physics do it. Let's look at a water molecule, one oxygen, two hydrogen. It's very simple, and we consider only a couple dozen of water molecules, and we want to know what's the ground state, what's the state with minimum energy of these couple dozen water molecules, and we want to know as temperature increase, what happens to this cluster, and what's the thermodynamic property of this system. So on the right side, I show you the ground state of water clusters like 20 to 30, and this is for different kind of water potentials. Basically, we just consider the Coulomb interaction between these point charge. That's the main part, but also there are some details I don't mention here. And this is the ground state, and if we want to get the thermodynamics, we want to calculate the density of state of the system. The density of state means that what's the number of configuration for each particular energy? What's the number of configuration? How many configuration can you get? If you get the density of state, you get the partition function, and in statistical mechanics, once you get partition function, you get everything in statistical mechanics. For example, internal energy, free energy, and specific heat, etc. So you basically get all thermodynamics. And let's have the density of state of these water molecules, a couple dozen water molecules here. And for only 6 water molecules, the ground state configuration, the difference between ground state configuration and the maximum energy state configuration is over 2 to the power 115. And for the size 30 water molecule, this difference between the high energy and the ground state energy, the number of configuration is already about 4 times 10 to the 118. And look at this number, why need to use high performance computing. And even with a supercomputer, you can't solve it with brute force. You need some clever algorithm and some sampling algorithm, some computing algorithm to speed up your simulation. So there's basically two types of approach to HPC. There are numerical methods and there are simulations. By numerical methods, I mean, for example, you can list the equation of the system, and for example, the Schrodinger equation for the system, and then you solve the equation numerically, or you can run some simulation, typically like Monte Carlo or molecular dynamics. Here I list two statistics table on 2 supercomputers here. Kraken is one of the supercomputers at the NIC Center, and Jaguar, now it's called Titan, is a supercomputer at Oak Ridge National Lab. I list the scientific library usage, as you can see on these 2 computers. The first one is the most cited library on both machines. It's a library developed by Cray, and it contains common scientific routines like linear algebra routines, etc. on this library, because both machines are Cray machines, so you're going to want to use this library in your calculation because it's well tuned. And there are also FFTW, which is fast Fourier transform. And because both machines using AMD cores, so the ACML, the AMD math library is also heavily used. So that's the usage basically on supercomputers, how the numerical method is applied. And now let's talk about simulation. there are a lot of community code actually you can use just on these two machines. You don't need to do any program actually, but you need to read the manual, of course. On backend, the most cited application is NAMD, which is MD code for biophysics. And the second one is PRS, I don't know. I think it's a weather code, and the third one is Amber, is also MD code for biomolecule. And on Jaguar, the first one is benchmark, doesn't count. The second one, LAMMPS, you can use that in your solid state physics calculation or some soft matter like a polymer calculation. Let's look at the actual CPU hour usage for this application. In 2011, on Kraken, the most time-consuming and the largest scale is actually a code called P-Gadget. It's a code it's an astronomy code, actually, simulate the formation of black hole. And the second one is the NAMD, it's the molecular dynamics code. And on Jaguar, the largest scale is the code called HMC, which is a quantum Monte Carlo code. And the most time-consuming code is S3D, which is a simulation of turbulent combustion code. So as you can see, basically, the cosmology and the molecular dynamics code and Monte Carlo code and weather forecasting code dominates the usage on supercomputers nowadays. And mention two simulation methods, molecular dynamics and Monte Carlo, and what are they? So let's give you an example to understand. Let's say we want to study an argon particle in a box, and we want to use first molecular dynamics method. Okay, we list the Hamiltonian, basically the energy function, which is kinetic part energy and potential energy, and then we solve this energy using Newtonian, just the equation of motion. The position of each article at time t plus delta t is related with its position at time t and t minus t and the acceleration. And the acceleration is from the Newton's second law. Of course, this force can also be calculated from ab initio calculations. So you solve Schrodinger equation, get potential and takes gradient. And in this case, if you want fix the temperature, then it can be realized just by rescale the velocity according to the temperature and kinetic energy. That's the simple way to do it, and there are more advanced and more advanced way to do that, molecular dynamics. And let's say now we want to solve the system using Monte Carlo method. In Monte Carlo, we generally ignore the kinetic part. We write the energy in terms of potential energy. That's because this is basically Monte Carlo is basically a random experiment with random number, computer experiment with random number. Let's say we pick up randomly argon particle and we then move it into an arbitrary direction. And we decide whether to accept or reject this move by comparing another random number with the transition probability. So the transition probability from one state to another state is related to the ensemble of your system. Let's say this is the canonical ensemble because of the fixed temperature, and then the transition probability is related with the energy change of this move and the temperature. And this is called Marchowitz algorithm. Of course, there are more advanced algorithms. Here, just to show you two simple algorithms, what is molecular dynamics and what is Monte Carlo. And there's a lot of popular code, community code you can use if you just want to get started and see how it runs. For example, for MD, as I showed you before, there's a NAMD, MD code for biophysics, and LAMMPS, MD code for solid state physics, and VASP, which is ab initio molecular dynamics. There's not as many as Monte Carlo code as MD, because as you can see, the advantage of Monte Carlo is that it's conceptually simple and easy to program. But the difficulty is there's no time, which means there's no dynamics. If you want dynamics, you want MD. But the advantage of Monte Carlo is that If you use the right algorithm, you can equilibrate your system much faster, which means you can simulate larger systems. There are two examples given. Sample code for HMC, which is a quantum Monte Carlo code, and TAPI, which is a Monte Carlo code that's used to study the phase equilibrium of fluids. For more information, you can go to this link, which lists the software installed on Kraken and the basic information on how to use it. So now let's see a specific example. The code is called WLS, and we use this code to study the magnetic properties of alloys at finite temperature. And it's a combination of thermodynamics and the first principle. Basically, the structure is like this. We have a master node which do Monte Carlo simulation, and we have worker nodes that solve Schrödinger equation, which basically is a specific equation of Schrödinger, specific type of Schrödinger equation for the system. Of course, we decompose the system into smaller parts and solve them in parallel. This is a general way how you parallelize your code. As you can see, for the dynamics part, it generates configurations in the collects energy for each configuration. And for the worker node, it calculates the energy for one specific configuration and send the energy to the node. In this way, this code can achieve quite amazing performance. Let's see. The y-axis is the sustained performance in T-flops, which is 10 to the 12 flops. Flops is floating point operation per second. And the x-axis is the number of cores. For a fixed problem size at 200 or 1000, we have an ideal scaling relation shown by this plot. And the peak performance is about 1.8 petaflops of this code, which is amazing. But on the other hand, you see the problem size we can consider is still less than 1000. Which, in another way, indicates the complexity of the problem we need to solve. So let me show how we apply this code to solve iron's magnetic property. We know that iron is ferromagnetic below Curie temperature and paramagnetic above temperature. So if you look at the experiment data of specific heat, there will be a peak where the transition happens. Of course, people try to reproduce that from the theoretical calculation, but there's always a gap. There's always difference between the theoretical calculation and the experimental data. And when we look at that, what we found is that in most of calculations, people assume that at this temperature, the structure of iron is still perfect BCC structure as indicated by this black sphere. But as a matter of fact, at 1000 Kelvin, you can expect that there will be lattice vibration near the equilibrium position. So there will be a thermal displacement for this iron particle. It's not a perfect crystal structure, but of course, include this information is expensive, computationally expensive. But if you consider thermal displacement, what happens is the magnetic moment on each iron atom is not uniform. Indicated by the magnitude of this moment is indicated by the different colors. So you will have a distribution of this magnetic moment. If you consider this information into your calculation, then what we found is that we can perfectly reproduce the experimental data as indicated by this triangle, and this red circle is the calculation without this lattice vibration. So the gap is the lattice contribution. This example basically confirms the triangle, Landau triangle, try to mention here. And it's a perfect example to show that how high-performance computing bridges the gap between the experimental data and the theoretical understanding. So hope by now you are convinced that the scale of problem in condensed matter physics actually requires HPC. And there are traditionally two types of approach, numerical method and simulation. And I show the two popular simulation methods, molecular dynamics and Monte Carlo. And another message is that even with supercomputer, and there's still a lot of work to do. And thank you for your attention.